Since risk is about the future and since there is no data about the future, only judgments about the future, then we should ask the question, how do we measure and manage risk? Risk measurement and management. This is part 2 of a 6-part series of videos on measuring and managing risks. Part 1. What is risk? What are the 7 factors necessary to measure and manage risks? Part 2. Estimating or measuring risks. Part 3. Measurement methods. Part 4. Analyzing risks. Part 5. Controlling risks. Part 6. Managing risks. Part 1 of this series of videos for risk measurements and management explained what constitutes a risk and introduced 7 factors necessary to measure and manage risks. A bow tie diagram was presented to visualize the relationships between a risk event, its causes, and consequences. In this video, we will address the scientific basics of measurement and how humans can be incorporated as measurement instruments to derive ratio scale estimates of the components of risk. Issue management versus risk management. Past events are issues. Future uncertain events are risks. Issue management is important. Recovering from losses already occurred. But issue management is not risk management. Closing barn door after the horse has escaped. Risk management may be even more important. Identifying uncertain future loss events requires human judgment, extrapolating from past issues, brainstorming, selecting controls to reduce future losses. Human judgment for estimating and measuring risks. Think of humans as input devices. Managers. Subject matter experts. Surveys of constituents. But care must be taken to convert human judgment into mathematically and scientifically valid measures that result in effective risk management. 4 levels of measurement. The level of measurement of a number conveys specific meaning and determines what mathematical operations may be performed that are scientifically valid. Nominal measure. In name only. Identification. No mathematical meaning. Ordinal measure. Conveys an order, high to low or low to high, for example, the order of finish in a race. Intervals have no meaning. Interval measure. The same difference or interval has the same meaning anywhere on the scale. Ratios have no meaning. 80 degrees is not twice the heat energy as 40 degrees, and 0 degrees does not mean no heat energy. Ratio measure. The ratio of 2 numbers has meaning. Ratio level measurements convey proportions. Relationships of the 4 levels of measurement. Each level has all the meaning of lower levels plus additional meaning. Ratio measures are the highest level in meaning and convey proportion. Ratio measures are the only level that can be meaningfully multiplied by one another. Multiplying ordinal numbers, a common practice, is mathematically or scientifically meaningless. Significance of measurement levels to risk management. Since ordinal or interval level measures may not be multiplied by one another for mathematically or scientifically valid results, and since risk is the product of likelihood and impact, ordinal or interval measures of likelihood or impact should not be used in estimating and managing risk. However, it is all too common for ordinal measurements to be used for risk management, resulting in questionable and often misleading results. Ratio level estimates or measures must be used for likelihood and impacts, for risk estimation to be scientifically valid and risk management to be effective. Common practice and common mistakes. Estimates for likelihood and impact are rarely ratio-level measures in today's practice of risk management. The most common practice is to multiply human ordinal judgments of likelihood and impact. Common practice risk map. 1 to 5 ordinal scales. Mathematically meaningless. What is the consequence of multiplying ordinal measures when estimating risks? The common practice of using ordinal measures for risk matrices results in risk estimates that are mathematically meaningless and produces arbitrary decisions and risk management actions. More specifically, the following shortcomings are a result. A. Poor resolution. Typical risk matrices cannot correctly and unambiguously compare many, for example, less than 10%, of randomly selected pairs of likelihood or impact. Identical ratings can be assigned to quantitatively very different risks. Range compression. B. Errors. Risk matrices can mistakenly assign higher qualitative ratings to quantitatively smaller risks. For risks with negatively correlated frequencies and severities, they can be worse than useless, leading to worse than random decisions. C. Suboptimal resource allocation. Effective allocation of resources to risk-reducing countermeasures cannot be based on the categories provided by risk matrices. With non-ratio scale risk measures, the selected controls to reduce risk will be suboptimal. Deriving risk measures from human judgment. Fortunately, there are methods for using human judgment to derive ratio-scale risk estimates that are mathematically valid and surprisingly accurate. These methods capitalize on the following characteristics of the analytic hierarchy process. 1. Relative rather than absolute judgment. 2. Eliciting redundant judgments. 3. Judging elements that are within an order of magnitude. 4. Structuring complexity in a hierarchy of clusters. 5. Using words instead of numbers for qualitative measures, such as the importance of objectives. One. Relative versus absolute judgments. Humans are more accurate making relative judgments than absolute judgments. Absolute measurement requires a scale, such as feet or meters. When making absolute judgments, one must try to picture what a unit on that scale is, and then estimate how many of these units are in whatever is being measured. Relative judgment does not require a predefined scale. Scales for subjective and qualitative objectives, such as preference for style, do not exist and need not exist in order to make relative judgments. Example of relative versus absolute judgments. Given images of two rectangular tables labeled A and B, one is larger than the other. Let's compare relative versus absolute judgments about their areas. Relative judgments. Table A is about 4 times the area of Table B. Relative judgments are easier to make and are more accurate than absolute judgments. We don't need to envision a foot-long ruler, or a yardstick, or a meter stick. Absolute judgments. We need to envision a ruler, yardstick or meter stick, and estimate the length and width of each of the tables, and multiply to get an estimate of the areas. Table A is about 20 square feet. Table B is about 5 square feet. Table A is about 4 times the area of Table B. Two. Redundant judgments. As explained in a recent book, Noise, A Flaw in Human Judgment, by Daniel Kahneman and others, human judgments include noise. The noise can be reduced, however. Aggregating multiple estimates can be very effective. The most common type of aggregation, Combining judgments from many people will be discussed in a later part to this video series. Redundant judgments, eliciting more judgments than the minimum required to compute estimates, and processing these judgments in an eigenvector computation, is very effective at reducing judgment noise. Redundant judgments and eigenvectors. Thomas Soddy, a world-renowned mathematician, recognized that redundant judgments, processed in an eigenvector aggregation computation, can significantly reduce the noise in individual judgments, resulting in improved accuracy of the estimates. The method later used by Larry Page as a key to Google's success consists of computing the normalized right-hand eigenvector of a matrix of pairwise comparisons. See the $25 billion eigenvector. The method has been shown to be remarkably accurate, provided that there is enough variety and redundancy in the elements being compared. When I first met Thomas Soddy, he asked me to hold a few rocks of different sizes, and estimate the relative weights of the rocks by comparing the rocks two at a time. As an example, suppose I ask you to do the same with 3 rocks, A, B and C. Suppose you judge that A is about twice the weight of B. And suppose you estimated that B is 3 times heavier than C. If you were fairly certain of your estimates, you wouldn't need another judgment to conclude that A is 6 times the weight of C. But suppose you continued with a redundant judgment, and compare the weights of A and C. And suppose you estimated that A was 7 times heavier than C. What? This judgment is inconsistent with the other 2 judgments, since to be consistent, you would have to have said that A is 6 times C, not 7 times. So is this third judgment wrong? Before answering that question, let's first assume that we have an accurate scale and can weigh each of the rocks without any error. In fact, each of the judgments has some error, and using all 3 judgments, which one is redundant is immaterial, in an eigenvector computation, we'll average the errors to produce a more accurate estimate of the relative weights of each of the 3 rocks. The more rocks or elements for which we are deriving measures from human judgment, the more the number of redundant judgments can be made, and the less noise we will have in our estimates. Inconsistencies introduced when making redundant judgments are allowed, and in fact can significantly improve the accuracy of the derived measures. There is a formula for the number of judgments when comparing n elements with one another. The formula is n times n minus 1 all over 2. So for example, with n equals 5 rocks, there would be 10 judgments. Since only n minus 1 or 4 judgments would be required, there are 10 minus 4 or 6 redundant judgments. Redundant in the sense of not needed to algebraically solve for the relative weights with only 4 judgments. But useful in that the results of the eigenvector computation with all 10 judgments will be more accurate. A validation exercise for you to validate that this works is presented at the end of the video. If we have n rocks to compare, there will be n times n minus 1, divided by 2 pairwise judgments. For example, with n equals 5 rocks, there would be 5 times 4 over 2, or 10 judgments. For example, with n equals 9 rocks, there would be 9 times 8 over 2, or 36 judgments. The greater the number of redundant judgments, the greater will be the accuracy of our estimates. However, the more effort there will be in eliciting the redundant judgments. We can organize elements into clusters of no more than 7 to 9 elements, in order to keep the number of judgments from becoming burdensome, as we will explain shortly. Judging elements that are within an order of magnitude. Humans are reasonably accurate in making relative estimates, provided the ratio of the comparison is within an order of magnitude. For example, consider human judgments about relative speed. Within one order of magnitude, approximately 10 to 1, humans can make relatively accurate judgments such as a sprinter or runner is going about 5 times faster than a couple walking a baby carriage. About 2 orders of magnitudes, more than 10 to 1 but less than 100 to 1, humans find it somewhat difficult to judge relative speed such as I think this car is going about 25 times faster than those walking nearby. 3 orders of magnitude. Humans find it very difficult to judge relative speed of several hundreds or 1,000 to 1. For example, unless you know that a turtle can walk about 3 miles per hour, and a supersonic jet flies at about 2,000 miles per hour, it is very difficult to judge the ratio of their speed. Four. Structuring complexity in a hierarchy of clusters. 3 reasons for structuring complexity in a hierarchy of clusters are A. Orders of magnitude. Humans are relatively accurate in making relative estimates provided the ratios of comparison are within an order of magnitude. When factors differ by more than an order of magnitude, a hierarchy is constructed by cluster and subclusters, where elements within each cluster or subcluster are within an order of magnitude of one another. B. Human cognitive limitations. If there are more than about 7 plus or minus 2 elements within a cluster, human short-term memory limitation results in an increase in noise of the judgments. C. Number of judgments. The number of judgments required, n times n minus 1, divided by 2, increases in proportion to the square of the number of elements within a cluster. Limiting the number of elements in a cluster to no more than 7, 8, or 9, results in fewer required judgments in order to derive an accurate ratio scale of priorities. Five. Verbal judgments instead of numbers. Verbal judgments, words, are sometimes more appropriate than numerical judgments. Numerical judgments for qualitative factors such as time is 2.7 times more important than money are difficult to justify. Verbal judgments are easier to justify, but are not precise enough for measuring risks. Verbal judgments are ordinal measures and are limited in their applicability for risk management. Ordinal numbers may not be multiplied. Ordinal numbers may not be averaged. This isn't saying they aren't averaged, and they often are in practice, but the average is mathematically or scientifically meaningless. For example, what is the average of excellent and fair? However, as we will demonstrate, verbal judgments represented internally with ordinal numbers can produce accurate ratio scale measures when they are elicited in a pairwise process with redundancy and variety, and processed with an eigenvector computation. You don't have to take our word for this, you will soon be able to see for yourself with an exercise at the end of this video, that the meaning of GIGO, garbage in garbage out, becomes garbage in, genius out. Where, in terms of levels of measures required for meaningful risk computations, numerical representations of ordinal measures, words, are garbage, and the ratio measures produced by the eigenvector computation are genius. The following fundamental verbal scale of the analytic hierarchy process has worked well in practice for well over 30 years. You can remember the words on one hand. Equal, moderate, strong, very strong, extreme, one, equal, 3, moderate, 5, strong, 7, very strong, 9, extreme, with intermediate values of 2, 4, 6, and 8, between the 5 words of the scale. Area validation exercise. Purpose: to demonstrate for yourself how verbal judgments can produce accurate ratio scale measures for qualitative or subjective factors. Exercise: you will be asked to use the verbal scale just described to judge the relative sizes of the 5 shapes shown below. Of course, this example is not qualitative nor subjective, but their objective measures determined with a ruler will serve as a benchmark for the measures you will derive with verbal judgments. Before making your verbal judgments, estimate the relative areas of the shapes normalized so they add to 100%. For example, A is 30% of the combined areas, B is so and so percent, etc. Record your estimates on a sheet of paper, so you will be able to compare your estimates using verbal judgments, not only with the actual values, but with your estimates using numbers, which should be better in this objective example, but let's see. After you complete your verbal judgments, you will be able to see your derived estimates, compared to the actual relative areas as determined with a ruler. Next, enter the following link on your computer, tablet, or smartphone. http://bit.ly/estimate with words. Note: a link to this appears in the description of the YouTube video. Then, restart the video for a discussion of the results and the significance of the experiment. Discussion. Other examples. Many other examples, validating the accuracy of estimating relative measures using pairwise comparisons have been performed over the years. In each case, the estimated relative measures were very close to actual measures in published references. For example, estimating the relative consumption of drinks such as bottled water, soda, beer, wine, and hard alcohol in the United States. Estimating the relative electric consumption of various household appliances, such as an electric range, a refrigerator, a dishwasher, an iron, and a hair dryer. You can set up your own experiments making verbal judgments such as estimating the relative distance from your city to New York, Los Angeles, London, Paris, and Tokyo, or any other set of cities, then check the accuracy of the estimates on Google Maps. You will be impressed with your estimates. Significance. The ability to derive ratio scale estimates from verbal judgments is useful in many ways, such as estimating the relative importance of objectives, which is subjective, estimating anything for which there are no actual scales, prioritizing body styles of different cars. Which body style do you prefer and by how much? Estimating the likelihoods of future events, likelihoods of future prices for a stock, likelihoods of various teams winning a competition. Baseball, basketball, hockey, football. Seasons. Playoffs. What other situations can you think of where deriving ratio scale estimates from verbal judgments is useful? What about measures for risk elements? Ratio scale estimates for the elements of risk management. An event. Causes. Objectives. 4 risk measures or estimates. Likelihoods of causes. Likelihoods of the event given causes. Consequences of the event on objectives. Importance of objectives. Pairwise verbal judgments for likelihoods of causes. Pairwise verbal judgments for likelihoods of an event given causes. Pairwise verbal judgments for consequences of an event on objectives. Pairwise verbal judgments for importance of objectives. This is the end of part 2 of a 6-part series of videos for measuring and managing risks. Part 3 will discuss a variety of measurement methods. Links to each part of the series can be found at professorforeman.com. Thank you for watching.